afternoon, and thank you for attending the Steel Joist Institute's webinar, Properly Specifying Steel Joists. My name is Michelle, and I will be moderating today's webinar. Today's presenters are Keith Judeman and Tim Holterman.
Hi, my name is Tim Holterman, and I'm with Can-Am Steel, and we will begin the presentation. Open web steel joists are an efficient, economical method of framing building floors and roofs, but there are some basics, and that's the intent of this webinar is to cover those. How to properly specify steel joists. We'll highlight some of the current codes and specifications that apply to steel joist construction and provide some insight in the best way to plan your next project and deal with a lot of the particular items in terms of loads and designations and that sort of stuff. Practical guidance will be provided to both avoid unnecessary RFIs and to maximize system economy. And you'll see a little graphic come up periodically throughout the presentation that sort of alerts you to specific items that we've seen generate RFIs and that are of interest to avoid RFIs in the future. The presentation will be in 3 sections. The first one has to do with codes, specifications, and designations, and I'll be doing that. I'll pass it to Keith, who will have quite a few slides about additional loads, both uniform loads and non-gravity loads, and then it will return to me to finish up with 3 subtopics: economy, responsibility, and tools. The basis for this presentation is the current Steel Joist Institute specifications. A quick word about the Steel Joist Institute. It was founded in 1928, and the first catalog and specification was published in 1932. So the current edition is the 44th edition, and it includes the document known as SJI 100-2015. That's the official ANSI designation, but that's the specification for K Series, LH Series, DLH Series, and open web steel joists, and for joist girders. Again, that's an official reference document, and the big change in this newest edition from 2015 was that where in the past there have been a separate specifications sections and wording for K Series and then for LH and DLH and then for joist girders, it's been merged into a single specification. There's a companion specification that is specific to composite steel joists, known as the CJ Series, and that's published separately in a catalog of its own. And then other SJI documents are the Code of Standard Practice, which supplements the SJI-100 specification, is in the 44th edition catalog, and then there's a separate Code of Standard Practice for the CJ Series that's included in that document. Other important documents that are sort of reference materials for specifying steel joists would be ASCE 7. And most projects these days are working with ASCE 7-10. ASCE 7-16 has been published and will be coming into force as IBC 2018 gets adopted, and Keith will touch on a couple things later relative to that. We still see a few projects come through that are making reference to ASCE 7-5 or 05. But I think it's time to move on from that one, and again, there's a new one coming up. Part of the reason to reference ASCE 7-10 or the ASCE-7 documents is that the load combinations, governing load combinations, are typically found there. We have the set of load combinations here for strength design or basically LRFD, and another set of load combinations for ASD. I'm not going to spend time going through all the details of those, but that's the importance of those documents. Other key references would be the International Building Code, which is 2015, or these are all governed by the local jurisdictions, so it varies a lot what may be in play in a particular part of the country. Not everyone has adopted 2015, so there's still a lot of older versions referenced, and then 2018 is now become available and will be referenced in the future. And the last document to reference in terms of just specification documents would be FM Global, which is factory mutual, and the requirements that they put out. So some of the projects that utilize joist and metal deck would be subject to some of their provisions and some of their papers. This slide is pretty wordy. I'm not going to read through all this, but it's just sort of the fundamental definition of joist and joist girders. So they're open web, in-plane, load-carrying steel members. The girders are used as primary framing members and supporting joists. And the next slide maybe says it better with a picture. We see that the deck has not been installed on this building. It's under progress, but we see the steel joist, which will be supporting the deck. We specifically reference a column joist because there's some particular specification in OSHA items that are particular to those column joists. And then the joist girder is the primary truss that's running typically from column to column and is supporting other joists. This slide is sort of an overview of the SJI Series, and this is available to you in your handout. I'm not going to spend a lot of time on it because we're going to go into more detail with each of these, but we'll be talking about K Series, KCS, Joist Substitutes, LH, DLH, and then we also have the Joist Girder series, and as I mentioned earlier, the CJ, which is the composite joist. So again, this is an overall summary with the depth and span ranges, but we'll start to get into some more details. All of the joist designations are established by their nominal depth, followed by the series, so K, LH, DLH as appropriate, and then by the section number designation. The section number designations range from 1 to 25, and the requirement or the way the load tables work is that the standard joist designations listed in the standard load tables shall support the uniformly distributed loads as provided in those tables, and that is the top or the black number as we look at the sample there. And then the red figures in the tables represent a uniform load that would produce an approximate deflection of 1/360 of the span. And then for each of these series, in terms of the non-composite joist for K, LH, and DLH, we publish these in both ASD and LRFD format, with the LRFD format listing factored loads. This slide just demonstrates when we're reading those load tables, there's a listing of the span length. And so what is the actual definition of span? This is included in the catalog, but shown here as well. So if we're dealing with a joist that's spanning from steel support to steel support, it's basically line of center to line of center of those supports. If it's bearing on masonry or a block wall or something like that, the nominal span would be figuring a 4-inch bearing length. The actual bearing length may vary or maybe more than that, but that would be considered an extension. So the typical would be to figure 4 inches. And then for design purposes, we have a work point or a center of the end reaction that is nominally figured to be 2 inches from each end of the joist. So our actual design length for the purposes of the calculations would be the span minus 0.33 feet. However, which is the 2 inches at each end. But the span directly is what's to be used to enter the load tables and establish the uniform load carrying capacity. This is a summary for the K series of everything involved there. We have designations from 10K1 to 30K12. So that's depths from 10 to 30 inches. The standard seat height is 2.5 inches. The range of spans is from 10 feet to 60 feet. And what's listed here is the range of loads. The lower bound really is not that significant, but the upper bound is worth noting of 550 PLF for ASD, 825 PLF for factored LRFD. And the maximum span to depth ratio is 24. That's taking inches to inches. So 30K at 30 inches deep times 24, then divide by 12, we get to 60 feet as a maximum span. Here's a similar slide for the LH series, which ranges from 18-inch joists to 48-inch deep joists. A difference between K and LH is that the K jumps through the increments of depths in 2-inch increments. The LH starts out with a 2-inch jump, but then goes on to 4-inch jumps, and then even greater as we get to some of the very deep ones. The bearing seat depth standard is 5 inches for the chord numbers up to LH17, so that encompasses all of the LH series. The spans go up to 96 feet long, and the load carrying capacities are a little bit greater than what we could find with K series, going up to 1,068 PLF for ASD and 1,602 for LRFD. DLH just continues on farther. So for depths from 52 up to 120, we have some variations in the standard bearing seat depth of 5 inches up to number 17 chords, but then increasing to 7.5 inches beyond that. The span range can go up to 240 feet, and the load carrying capacities are, for for the standard tables go up to 1,304 PLF for ASD and 1,956 PLF for LRFD. We'll talk a little bit later. Obviously, when we get to 240 feet, we're shipping that in multiple pieces. It's typically manufactured as a single unit, but then broken down with a field bolted splice and shipped in parts. For LH and DLH series joists, there are some multiple possibilities for profiles, and the most common would be a typical parallel chord joist, but they can also be provided with a single pitch, a double pitch, and then they could either be a traditional underslung with those bearing seat depths that I mentioned earlier, or a bottom chord bearing and with a square end, or even the possibility of a cantilevered square end to extend out and create an overhang. The chord section numbers, what is the significance of those? So we see this excerpt from a table, and we have 24, K4, K5, K6, etc. There's not any, those are really just an indicator of the column, so they don't necessarily imply a specific chord section size for all the spans of a given designation. Some of the tables were built around a given chord angle size, but that sort of breaks down or isn't necessarily the case when we get to shorter spans. Something to make a quick note of is that for K-Series, not all sequential chord section numbers are used. So the example excerpt here is of the 24-inch deep joist, and we see that there's no 24K11. So occasionally we see that pop up on drawings. Maybe somebody had thought, I want something a little more robust than a 24K10. I'll just go to the next one. But in fact, a 24K11 doesn't exist, and that would surely generate an RFI. Another quick note is that when we get to short spans, there's really two notes here. The 8K1 designation used to exist but has been eliminated. So we see that specified on this particular drawing snippet, but we suggest either using a 10K1 or a joist substitute. It's pretty rare that the headroom is so critical that a 10-inch deep joist can't be accommodated, and the 8-inch would do the trick. So the 8K1 was eliminated just for simplicity of manufacturing, and a joist substitute, which the subsequent slides will provide us more details on, but we see at the bottom one of those is called out as a 2.5K3. That's a decent alternative. This is just sort of an accident, but the idea of joist substitutes is to use them for short spans. So I guess that's why we have pretty short little lettering there to say joist substitute down at the bottom. So the joist substitutes can be used where an open web traditional steel joist might not be applicable. The standard bearing depth and depth all the way along the length is 2.5 inches deep. It is possible to build them with special seats or deeper depths, depending on what the needs might be. They are intended for spans of 10 feet or less, and the designations are pretty limited. There's only 3 types, but they can easily be doubled up to obtain any capacity that's needed, or more capacity than what will be in the load tables. So the types offered are simply a 2.5K1, K2, or K3, and some samples are shown here of how we might go ahead and construct those, which could be using some angles or a hot roll channel, or it could be a cold form shape or a piece of HSS steel. Another part of the joist system is bridging. This slide just gives a quick overview of some different types. We may have bolted diagonal cross bridging. We may have horizontal bridging, which is run continuously through at the top and bottom chord levels. And then uplift bridging is a specific subset of horizontal bridging where it is to be placed adjacent to the first bottom chord panel point and only at the bottom chord. A few notes about bridging. The SJI specification provides a table for the minimum number of top chord bridging rows, and that's keyed by the chord section number and the span. There are shaded areas of the load tables, and that's an indication where bolted diagonal bridging would be required in lieu of welded horizontal bridging, and that's to meet stability and OSHA requirements. And then the Code of Standard Practice is where we provide tables for the actual bridging member sizes, and that's the variables there are the type of bridging, the joist spacing, and the chord section number, and the joist depth. Joist girders, a quick summary page here. Those are available in depths from 20 inches to 120 inches. The standard bearing seat depth is 7.5 inches, although there are cases where it will increase, and we'll get to that, I believe, in the next slide. The panel point loads can vary from 4 kips up to as much as 56 kips for ASD and 84 kips for LRFD. The self-weight can be as much as 200 PLF. There are some different web configurations that are possible, which are going to be touched on momentarily. And then for the designations, we have the depth, the number of panels, and the kip loading. And I'd like to point out or make note of the bottom of the slide, which indicates a suggestion that if it's an unfactored ASD load, that a K can be used just to indicate it's 9 kips. But then if it is an LRFD factored load, we suggest replacing the K with an F so that the 13.5 would be obvious that that is a factored load. Here's the joist girder weight table, and this gives the estimated self-weight for different combinations of the span, the depth, the number of panels, and the panel point kip loading in either ASD or LRFD. And we see that there's a gray shaded portion off to the right-hand side. So this weight table does not cover every combination of span, panel spacing, and kip loading, which has become too cumbersome because there's many combinations. However, a joist girder can be specified and used that fits with any of those gaps that are in the weight table. The weight table is just a guide to self-weight. It's not a restriction on those being the only designations that can be provided. The weight tables are based on a maximum chord angle size of 8 by 8 inch angles, and so the gray shading in the weight table indicates where the bearing seat depth should be increased from 7.5 inches deep to 10 inches deep as a standard. There are some different ways to configure a joist girder, and this D/S ratio would be the depth of the girder relative to the spacing of the joist. So what we see here is the top example is pretty rare, where we'd be putting multiple panels between each joist spacing. The second one is the more typical, where the joists sit at the diagonal intersections of the top chord, and that's what's presented in the picture. There are some alternate designations. One is known as BG, and if that depth to spacing ratio gets high enough, it may make sense to load both the diagonal panel points and the redundant or intermediate vertical panel points as well. So the B sort of stands for both, that we're loading at both locations. Another alternate is what's called a VG, which would be to put the joists at the vertical members, and what this does is create some bigger openings for ducts. Actually, the opening in the girder is the same, but the advantage here is that opening is now shifted to be between the joists instead of having the large opening that would run into the bottom chord of the joist that it's supporting. So a note here is that unless a specific geometry is required, simply designating G is the best way to go, regardless of the depth to spacing ratio, and that will allow the joist manufacturer to make the most economical joist. So if there's if the VG is specifically required for duct clearance, then it would make sense to call that out. But in terms of if there's not a specific requirement to have one of these profiles or geometries, then it's best to leave it to the joist manufacturer's discretion and to obtain the best economy. KCS is a particular subset of the K series joists. They range from a 10 KCS1 to 30 KCS5. Other than that, the span and depth is similar to K series, and the maximum uniform load is similar as well. What's different is that these are based on a constant shear capacity, not shear due to uniform loads. So the minimum shear is equal to 100% of the shear capacity. All the webs are designed for compression and tension, except for the end web. These are parallel chord only. We publish a gross moment of inertia that can be used for deflection checks, and they could accommodate a single concentrated load not to exceed the shear capacity in the tables. And overall, they're versatile for non-uniform loads and loading requirements, which may change over time. So if it's a tenant space that's subject to new tenants and changing conditions or equipment, these provide an envelope of capacity that could be rechecked in the future. So it's an envelope of moment and shear capacity, and we see the moment and shear diagrams there and a little excerpt from the table. One important to note thing to note is that while KCS joists can accommodate concentrated loads and the envelope capacity makes them convenient to use for non-uniform loads, there is not a provision for concentrated loads away from panel points. So struts would still be required for a load in the middle of a panel, and Keith will touch on more on that later. Also, while the KCS Series joist would be checked specifically for uplift loads, they shouldn't really be called an SP or we shouldn't have a check for other loads. The idea is to pick it for an envelope to cover all of the anticipated loads, or else utilize a load diagram to express those loads. But trying to do a combination of picking the envelope and then still adding some additional loads is not recommended. Load over load designation. This is important and very common. It's called an alternate method. I'm not sure that's really the best terminology because, again, it's very commonplace. But the idea is that instead of picking an arbitrary chord number, we can dial in a more specific designation by prescribing a total load and a live load. So an example is 24K300/175, where it's 24 inches deep. It follows the K-Series rules, but it needs to support a total load of 300 PLF and a live load of 175 PLF. To help when specifying the load over load designation, the SJI publishes a weight table that gives some guidance in terms of bearing depths and bridging requirements. So those can be found in the weight table. And the key thing to note is that the weight table extends the maximum uniform load capacities beyond the standard designations, principally for spans up to 60 feet. We go as high as 2,400 PLF ASD, 3,600 LRFD, so that can be useful for many floor loading scenarios. So if we recall, the maximum for K-Series was 550 PLF, and that could easily be exceeded in a floor loading condition, but the load over load joists give us another option. I mentioned composite joists earlier. That's the CJ Series. They utilize shear connections to create composite action between the joist top chord and the overlying concrete slab. Here's an example designation. It has 3 loads behind it in sort of load over load format, where we have a total factored composite load, and it's a factor load because the CJRO is LRFD. Then we have a total factored composite live load, and finally the total factored composite dead load. So we're making a distinction between dead load that is non-composite as the concrete cures, and then dead load that may be applied after that, which is composite dead load. One important note is the CJ Series joist stretches the maximum span to depth ratio from 24 out to 30. Another quick note coming back to the red numbers in the load tables. Again, those are a capacity for checking or indicating a live load capacity, and these can be, they're based on a 1/360 limitation, but then if the rule is L over 240 or it was L over 180 or any other requirement, those can be prorated and linearly extrapolated for other conditions. And finally, on seat depths, the current SJI specifications are for the combined K, LH, and DLH series joist. So there are definitely overlaps between some of the K series designations and LH series designations, and there's no longer a fundamental design difference. But it is worth noting that the standard bearing seat depth is different at 2.5 inches for K and 5 inches for LH. So in terms of using, say, a load over load format or having a special loading condition, a good rule of thumb is that the maximum end reaction for a K-series joist that's going to have 2.5-inch deep seats should be limited to 10 kips or less. And in general, special depth bearing seats are far less expensive than seats that aren't deep enough. So if we have to start coping, say, a 3x3 angle to make a 2.5-inch deep seat, that is cumbersome, whereas providing a 5-inch deep seat for a K-series joist is not a problem. Or again, if the reaction is over 10 kips, it would be best to specify an LH series joist.
Good afternoon, everyone. Thanks for joining us. I have the second portion of this presentation. So additional loads, non-uniform and non-gravity, and we'll get right into it. So starting right off the bat with concentrated loads, and even though this seems sort of the simple and basic, it actually leads to a lot of RFIs and questions and sometimes a more misinterpreted topic, so we'll cover that. The SJI specification provides a default detail for field-added struts, as you can see here. So you'll notice it calls for the specifier determines the strut size, the connection, the point load magnitude, and the location limits off that panel point. SJI did not determine that. So the joist manufacturer will adjust the detail on their placement plans to reflect, to match the contract documents with the specific information. So SJI just sort of gives the basics, and then the specifier fills in the blanks. The SJI does provide guidance on the concentrated load not placed at a panel point of what magnitude load then requires a strut. So we call that the 100-pound rule, and on the screen is excerpts straight from the SJI specification for nominal concentrated loads between panel points which have been accounted for in the specified uniform design loads. A strut to transfer the load to a panel point on the opposite chord shall not be required, provided the sum of the concentrated loads within a chord panel does not exceed 100 pounds and the attachments are concentric to the chord. So they're saying that limit is 100 pounds, but that's just guidance from the SJI with the 100-pound rule. And as you can see, this is an example of a section out of a set of contract documents. So it's a sample detail where the guidance is given. The guidance is given that stiffeners, they're calling them stiffeners, but struts or stiffeners or braces are not required for the following conditions. So point loads less than 250 pounds on the top chord or less than 100 pounds on the bottom chord. The joist manufacturer will take that information and put that on the placement plans and will not analyze for local bending effects of the top chord for let's say a 240-pound point load at the top chord or a 90-pound point load at the bottom, and anything above that requires field-added struts in the field. Another example, this is just out of structural documents, and you can see it provides limit range for that concentrated load of 150 to 500, and then it also provides a dimension of 6 inches from a panel point. So a web stiffener is not required for a 140-pound point load, and the joist manufacturer is not going to take any local effects from that point load. And this is the example of the joist placement plans and what their detail looks like. It's a reflection of that structural document where the 6-inch dimension is input and the 150-pound limit requiring the strut is placed. So then the question is, how can the specifier have the joist manufacturer analyze for local bending effects of point loads that will be placed on joists and not have field-added struts installed? So what are some options there? And the next slide does not answer that question, but it begins to answer the question. We'll go over some steps and what options the specifier has on addressing those concentrated loads. So going to Code of Standard Practice, it provides 5 methods or options to specify a joist, and the goal of these options is at the bottom here for the estimator to be able to price the joist manufacturer to be able to properly design the joist per the documents, and then the owner to obtain the most economical joist. Option 1, Tim already covered on this, and it's the basic option of the standard designation pulled out of the catalog. So if you've got a dead load of 20, a live load of 30, so your total load is 50 pounds per square foot, joists are spaced at 5 foot on center, your uniform load on that joist will be 250 PLF total load, 150 PLF live load. If you go to the economy table, for this case, we're looking at a span of 25 feet. So you go to the 25-foot span and you come across until you find something that meets those minimum load requirements, and you've selected a 16K3, option 1. Option 2 is taking that standard designation, and then the standard designation covers the uniform loads, and then the note of joist manufacturer shall design joists for additional loads and locations shown. So that's giving the option, if you have maybe a rooftop unit with the exact loads and locations known, you can place that on the plans, add a note similar to shown here, and then the joist manufacturer will design for that standard designation or the load over load designation, and then in addition to design for the additional loads shown on the plans for those locations and account for that. Here's an option of taking option number 2 a little too far, so I've rewritten this note from a set of drawings in bigger font. Joist manufacturer shall design the gym joist for the typical roof loads indicated on S000, the applicable drift loads from the gym roof snow drift diagram on the sheet, concentrated loads from the rooftop units, and any other miscellaneous loads on the joist, including but not limited to basketball backstops, divider curtain, screen wall supports, kickers, etc. So clearly this is going to lead to a lot of RFIs and the joist manufacturer not knowing exactly what all needs to be covered. The specifier needs to define what loads need to be addressed in that joist design. So, but then the question is, sometimes the joist, even the specifier doesn't know all of the exact loads and locations, wants to have some flexibility for locations of loads or flexibility for future loads and locations, and what are some options there. So before we go to option 3, we want to start with SJI provides a way of addressing the definition of concentrated loads. And there's 2 terms that SJI has in the specifications, an add load and a bin check load. So an add load, a single vertical concentrated load that occurs at any one panel point along the joist cord, and it's in addition to any other gravity load specified. So it's an additional load at any panel point. A bin check load is a vertical concentrated load used to design the joist cord for additional bending stresses resulting from that load being applied between 2 panel points. So it's a local design check, and it's not in addition to. So this load shall already be accounted for in either the joist designation, a uniform load, an add load, or other. And this is only doing a bending check to check for loads that have been accounted for, but you don't know exact location, may induce stress, and then don't need an additional field added strut. So just sort of a visual definition of this, an add load is at any panel point going across the span, and then a bin check load is a concentrated load between panel points, checking and bending, so it can be on the top chord or the bottom chord, or both top or bottom. That leads to option 3 from the Code of Standard Practice, is that you can have the application of an add load and bin check load in the specifying the joist on the documents. So this gives some options of how we would word that. Note that you designed for a magnitude concentrated load located at any one panel point along the joist. So that would be how you would word an add load. So that's, you can either word it that way or call for an add load. Option B, designed for additional bending stresses resulting from a certain magnitude concentrated load located at any location along one of the chords or both of the chords. This is a bin check. So either that sentence written out or simply bin check can be noted as that also. You can combine, so C is combining A and B, where you're specifying both an add load and a bin check load. So you've got a future allowance for rooftop equipment or additional loading. You can have that add load and the bin check load. So SJI even gives some situations or scenarios of how you might how you might use an add load or bin check load. And the examples, one would be the specifier has selected a joist capable of carrying a 500-pound RTU. So the designation has accounted for that. However, the location is not yet known, and wants some flexibility on locating that load without a field added strut. You can call for a 250-pound bin check load for that 500-pound RTU. So the point loads are far enough apart that they won't land in the same panel, and the joist has already been designed for that. All we need is a bin check. If the standard joist, so that second bullet, the standard joist specified, has been specified but is not selected to accommodate an RTU load, then you have the joist and you specify both a 500-pound add load and a 250-pound bin check. Another scenario is that you might have accounted for loading through a collateral load or an additional dead load. And so you've accounted for that uniform collateral. You just know you'll have local hangers or point loads, and you can specify just a 150-pound point load from incidentals to be designed for without a strut, and that would be a bin check load. So going back to that question, what gives us flexibility on designing or accounting for point loads without struts? it would be this add load, bend check load combo, or at least just the bend check load. One scenario, this is an example from a set of contract documents where the bottom chord of the joist shall be designed to carry a 500-pound point load at any point along the bottom chord, and this load condition shall be combined with the following uniform loads. So we're given uniform loads and told a 500-pound point load at any point along the bottom chord. Then this is just a snippet from the framing plan, but in general, the framing plan used all standard designations and showed standard designations. And that would lead to an RFI for sure, because a couple of questions that this leads to is, one, is the 500-pound load at any panel point? It says at any point, or is it any location? Is it an add load or just at panel points, or is it a bend check load that it needs to be accommodated local bending effects? What loads were considered in the selection of the standard designation? So does the 12K5 already account for the 500-pound point load, or in the selection of that standard designation, or is it a 12K5 has been accounted for the uniform load and there needs to be an add load and bend check load? So clarification on that, SJI provides definitions there of how to approach that. Option 4, KCS joist. Tim already talked about selecting KCS joist in the definition. Keep in mind that in the top line, it says KCS joist, you select them using a moment and end reaction and shear, constant shear, without specifying added loads or diagrams. That's key. And also note that Tim already touched on this, but does not preclude you from needing field-added struts at concentrated loads not located at panel points. This is an example from a set of contract documents where, and this is common, that you'll see KCSs that are called for, and then either in sections or on plans, there's additional loads noted. And all those loads should have been considered when selecting the KCS joist, and that can lead to some confusion. Is this supposed to be in addition to, and whatnot? So KCSs end up with a lot of RFIs, and that's why Tim even referenced, avoid calling them KCSSPs. This next slide, refrain from creating an LHSC. So I see that quite a bit where there's a KCS series, but the LH doesn't have a corresponding constant shear series with it. So sometimes people can be creative, and in this case, they've got some 32 LHO6s, and then they've got some SPs with the RTU, and say that the LHSP shall have a constant moment capacity and constant shear capacity. And in this case, you'd rather, I'll get to the next slide of how to handle that better. The other thing that you don't want to do is say, okay, if we're going to avoid creating an LH constant shear joist, don't mix KCS with LHs. So sometimes you'll see 32 LHO6s, and they might throw some 30 KCS series in there to get that constant shear. Not recommended. It's not the most efficient approach. And really a better approach just for this condition would just be to have an add load and a bend check load. So you're going to have a future RTU, which joist this is going to be applied to. So if you just have an add load for the maximum total weight that RTU will have on a joist, and then a bend check load for that point load, you'll do two things. You'll actually have a more efficient design than trying to create a KCS. It'll be clearer for the specifier, and actually in this case with the bend check, then you don't even have to worry about the field added strut when that RTU is located. So that would be the approach there. Option 5 is if you've got a lot of different point loads and snow drifts, really the best approach is probably just to provide a load diagram. So option 5 is just an all-out load diagram with all the loading that needs to be applied to the joist and the locations. You can also combine this with add load, bend check, where again, if you don't know those locations, you've got a load diagram showing all your snow drifts and locations or loads that you do know, and then you can still have add load and bend check load on top of that. So the benefits of following this is busy and a little bit of small font, but a snippet of a framing plan where there's some standard designations called out on here, 56 DLH15s, but then you also have rooftop units, and you've got screen wall, refer to typical detail, And then there's even additional notes where it says design joist for support reactions resulting from 30 PLF divider curtain weight. So this will lead to RFIs inevitably, and that what loads were accounted for in the DLH 15 designation, what additional loads need to be accounted for. And keep in mind that the lines here, the portion of the SJI spec that I've re-entered on this sheet says that you want to use one of the 5 options because it allows the estimator to price the joist manufacturer to design the joist accordingly, and really most importantly, the owner to obtain the most economical joist. Moving on, I want to touch on special deflection limits. So we're applying special loads. Oftentimes we run into special deflection limits, and in this case, this is just a little portion of framing plan that shows some 96 DLH 21s with folding partitions crossing them. And the general note says, limit the 96 DLH 21 joist to snow or live load deflection to 1 inch max. So what happens in this case, in this specific case, the 96 DLH 21 spanning 116 feet, and just it weighs 80 pounds per foot, the self weight of that joist. We'll reference that later, why I put that in there. But the load from the table, the standard load from the table for this designation is 1149 PLF total load, 877 live load. For these joists spaced at 10 feet on center, that basically gives you a 115 PSF total load, 88 PSF live load. We know that live load out of the table gives an L over 360 deflection. In this case, for the 116 feet, it was 3.86 inches. So to limit that live load to 1 inch becomes a real challenge. And even with 8x8 by 1 inch chords, the largest angle a joist manufacturer could even possibly supply for this joist, and almost triple the weight of the joist, thus tripling the price and the cost, and still you still cannot reach a 1 inch limit for that 877 PLF or that 88 PSF live load. So, but in this case, really the specifier only intended that the joists are checked for a live load of 20 PSF. So in that case, at 10 feet on center, it's only a live load of 200 PLF, which is a fraction of the live load, the L over 360 live load from the table. And in this case, just the standard designation, if you prorate that 200 over that 877, multiplied by that over 360, the live load deflection for 20 PSF is only 3/4 of an inch. So the live load deflection limit's actually met by the standard designation without any additional considerations. And that's a check that you can do. Tim was talking about the tables and that red number being the live load. So that's a check the specifier can do and avoid the RFI. Or if you do have deflection live load limits, you still want the joist manufacturer to account for and check, it would be to provide the exact loading, live loading, or loading requirements that you would want checked for that condition. Determining net uplift for joists. So next section is looking at uplift for joist, and from the SJI Code of Standard Practice, specifier needs to provide all applicable loads, and I circled here that net uplift is one of those required. And what does that mean? So keep in mind that ASCE provides formulas for design wind pressures and net design wind pressures. These are not the same as the net uplift required by SJI. So AISC net is the sum of internal and external pressures. SJI net uplift is the final resultant pressure of a load combination in combination with dead load. Wind uplift is a design consideration, should be specified as net uplift on the steel joists and joist girders. And then the chart on the following page is an example of what one might find on structural documents, and this will lead to RFIs. So the questions will be, what loads does this represent? And is this, a gross uplift or a net uplift, or does it need to be put into load combinations? So it leads to what exactly are these pressures shown. Keep in mind that roof pressures need to be converted to a net uplift or the resultant of that load combination. And in that load combination from ASCE 7, Tim showed them earlier on an earlier slide, but dead load's a part of that. But keep in mind that there's really kind of a maximum dead load or a minimum dead load that the specifier knows. That maximum dead load is the maximum that you want to account for gravity loading. that minimum may not include those collateral loads or other dead loads that may or may not be there in the final design, but would be a consideration for net uplift. The specifier knows that better, so it really needs to be clear on the documents. Joists are considered components in cladding. Girders are considered part of the main wind force resisting system, so they really do have two different sets of uplift to consider. This is an example of what a net uplift plan might look like for joist, where the note at the bottom here, not only does it provide the net uplift and pressure, but it even clarifies that the net uplift shown is the resultant of the load combination of the 0.6 wind plus the 0.6 dead. So the joist manufacturer's clear that that's already been accounted for in the numbers provided. If there is a different uplift diagram for girders, it would be shown like this. It would be a slightly different, but similarly for girders. Another way of handling this is if there is a chart with pressures and a diagram just showing the zones, the uplift zones, at least this chart shows note in that it's the gross uplift pressure, and then note 2 on here is that the joist uplift load combination is 0.6D plus 0.6W, use a dead load of 12 PSF. So the joist manufacturer is more than capable of doing the math as long as we're clear on what load combinations and loads to use. And another example of where it would just lead to RFIs, we just have a wind pressure table, and one says the positive acts down, and note 2 says the negative pressure acts away from the surface, but still not clear on exactly if that's net or gross and what to do from there. That would lead to RFIs. ASCE 716 is coming, to mention that before. So what does that mean? The ASCE 710 wind loads, we're all familiar with kind of the zones. We've got a field and the edge and the corner zone, 3 basic zones on our roof. And that can be complicated in and of itself if you've got just a sample roof framing plan here of how busy it can be, and it's about to get a little worse. So ASCE 716 adds an additional zone or edge zone, if you will, and the corner now becomes an L-shaped, and so the charts and loads become more complicated with ASCE 716. I say more complicated, just busier, and something to be aware is coming. Next force to consider is rollover forces on joist seats. So basically, you've got a continuous angle that the deck is welded or screwed to, and then that angle is attached to the joist, and that's your diaphragm chord. So this is an example of what that would look like from a set of structural documents. You've got a 3x3 diaphragm chord that the deck is attached to that. That's the 3x3 angles attached to the joist. But the 3x3 angle is not directly attached to the wall. Therefore, it would lead to, or it would cause a rollover force in that joist seat to transfer that load down to the supporting structure. And it would look like this. So looking at this in view of the joist, you would have what we call a rollover force, and that force should be noted on the design documents or structural documents as a design requirement. And this is what that would look like in the field, an example of what that would look like. And the rollover force should be noted on design documents, but as a reference, 500 pounds or less will not really affect the design or cost or add any cost to the joist. Rollover forces up to 1.5 kips are typically handled with thicker seat angles or more a thicker seat, and adds a little bit of cost for the weight of that material, but not so much in the way as, or not as much in the way of manufacturing, just more material. But once you get above 1.5 kips, it can start to require seat stiffeners, as shown in the picture. And that adds more than just the material and the weld. It's really more of a handling issue in joist shops, and so there's a little more cost involved with that charge. So just kind of keep that in mind for rollover. The next item we'll talk about, more on rollover. There's other ways to handle rollover. If you don't want to go through the seat, you can collect it and put a channel or a tube between joist seats, and that's a way to really drag that force from the diaphragm chord down to the supporting structure without even creating that rollover in the seat, if you do have those high rollovers up to 1.5 kips. Keep in mind that tubes provide a wider surface where a better chance of hitting that low flute on the deck. There's a channel there's a chance if you use a channel that that could be an issue where you miss that low flute. Even if the roof is sloped, you can there's still ways to avoid just the rollover force on the seats. You know, in this case, there's a bent plate to accommodate that. Axial forces. So chord forces are carried as additional axial loads by the top chords of joists and girders. They may vary from one end of the chord to the other, and the additional axial load for each joist must be indicated. Type and magnitude of axial forces at the joist and joist girder end supports shall be shown on the structural drawings, and avoid resolving them through the seat connection. So this is an example. You've got the force, and you can see on the left, you're transferring this axial force, and it's going to transfer to the joist on the right, and you can see this gap between the joist and even in the chords of the girder seat, and the load path of that force has to go down to the cap plate and all the way back up, and can create some issues. So we want to avoid that. We'll show a little bit, we'll show a way to avoid that here in a few slides. Another thing to think about is when you've got those axial loads, it's noted on the framing plan, they tend to, you'll see them move up, and sorry, the circles look like they're, there we go. You've got the axial loads are transitioning, and they're increasing as you're getting to that collector brace bay. So they're starting a low number and going up to the brace bay where you have the larger axial force. Keep in mind that where that starts at an end connection at a wall, that it's helpful to show the magnitude if it's 0 at the perimeter, so that you avoid, the joist manufacturer avoids trying to have to start that 9 kips at that end joist at the wall where there's no way to transfer that force directly to the top chord. So show where the load starts and where it starts to accumulate and where that's 0. And then again, we're talking about this axial load transferring, and avoid going through the seat. You can see that the axial loads and the end moments should be tie plates or tie angles to avoid the eccentricity of the forces through the chord and the bearing seat. So you can see that eccentricity from the bearing condition up to the neutral axis of the chord. That can be accommodated through maybe a tie plate placed on top of the joist in the field to transfer that force, or joist tie angles. And a cross section of what that would look like is the orientation of the tie angles to avoid the end webs of joist or girders. And that you can, this allows the field to insert the tie angles and then miss the web members, and then have a downhand weld the field to the toes of the chords. So sometimes these collector forces are transmitted from the joist and they go to a braced bay. And so you end up in a braced bay, and those connections then transferring to that braced bay is more attention needs to be played on how that joist connects at that column cap plate. So in this case, it shows a typical detail of the braced bay, but it does not show that you may have a joist on the other side of that braced bay instead of a beam as shown. So in this case, it shows a braced bay with a joist in section 3. And if you look at that more closely, you can see that the joist is bearing on the face of the column, so the column extends up. The joist is not on top of the column, it's at the face of the column, and a cap plate or a tie plate is welded on top of the joist to the top of the cap plate, and that allows that transfer of that collector axial force from the joist to the cap plate into that braced bay to accommodate the braced bay. Rigid frames, end moments. The specifying professional is responsible for the rigid frame design. The type and magnitude of end moments at the joist and joist girder end supports shall be shown on the structural drawings. Avoid resolving joist or joist girder end moments through the bearing seat connection. The top chord details can be similar to those shown for the transfer of axial loads. And the top and bottom chord moment connection details shall be designed by the specifying professional. The joist designer shall furnish the specifying professional with the joist detail information if requested, unless specifically designed and detailed as when only flexible connections. Rigid frame action will induce a live load moment, which needs to be specified. So you have that live load moment now that you've got that fixed end condition on a joist or girder, and needs to be considered.
Okay, we will finish with 3 subtopics, which are economy, responsibilities, and tools. A good rule of thumb for economy, and a phrase within the industry, is deeper is cheaper. So if we take the global bending moment and consider that as a couple between the joist top and bottom chords, then for our global moment of WL squared over 8, the deeper the joist is, the larger that couple distance is from the top and bottom chord, and we'll get smaller chord forces and we gain economy. Now, while that is true, the deeper is cheaper, there's a point of diminishing returns as we increase the depth. So here's some general recommendations. For joists, a span to depth ratio of 18 to 24 is common. And with more economy, as we get nearer a ratio of 18 than say 24, obviously this is going to depend on the headroom that's available. As far as a point of diminishing returns, if we get to a span to depth ratio approaching 12 or less, then for typical roof loads, that would be beyond the point of diminishing returns. So say, for example, a 30-inch deep joist and a 20-inch span is getting beyond the point of gaining economy by being deeper. That's for roofs. For floors, that would change a little bit as we got to more loading. Something to be aware of is that for joists, and I think I mentioned this earlier, the current SJI combined specification blends the rules for K series and LH. So there's no real advantage to K versus LH and hey, where some of these series overlap. So if headroom will allow it, going beyond the K series to a 32 or 36-inch LH series joist could be real economical for spans of 50 feet and greater. And many manufacturers will produce a 32-inch LH joist on the very same production line that they're building K series. So it may make sense to take advantage of a couple inches of additional depth. For joist girders, the first rule of thumb is about a depth in inches about equal to span in feet, which would be a ratio of about 12. And that's a good starting point. A little bit deeper can add to some more economy where available. A note about joist depths is that joists are built, bundled, and shipped by depth. So on the left-hand side, we see a picture of, I think that's actually a couple of joists in a welding pit. So they've been stacked there to help economize some of the movements between each panel point and each weld. And bridging is also easier to install for joists of the same depth. On the right-hand side, we see a bundle at a job site. So even though, hey, for a certain situation, maybe the joist that has a rooftop unit and has a larger applied load, or let's say we get into a skewed corner of the building where the spans vary, to gain a couple PLF in potential self-weight of the joist would be offset by making too many changes in terms of changing the depth. So again, in a skewed corner, it would not make sense to jump from stepping down from a 24K to a 20K to an 18K to a 12K, maybe make one jump in the middle and then go to a joist sub for the very shortest ones in the corner. A note about rectangular bays. The most economical framing direction is going to be to run the joist in a long direction and span the girders in the shorter direction. This picture isn't really specific to rectangular bays, but it's kind of interesting. Shows an apparatus there and joist being erected, panelized erection where an assembly was made on the ground and then lifted up. With regard to deflection, avoid imposing total load deflection requirements unless they're absolutely required. Joists are built with standard camber, and the standard camber up to a span of 100 feet follows a radius of 3,600 feet, and then beyond 100 feet, the camber is a little less than what that radius would produce, and it follows an arc of span over 300. The SJI and the International Building Code do not specifically require a total load deflection check for cambered steel members. So really there's no reason to specify a total load deflection requirement unless there's some very specific need that the camber will nominally offset dead load deflection. A couple of notes about the self-weight of joists and joist girders. When specifying joists, always include the self-weight of the joist in the bridging. So if it's the load over load format or in selecting the standard designation, the self-weight should already be accounted for. 3 PSF is a good and reasonable number and for typical joists, and there's not a lot to be gained from trying to fine-tune that to 2.7 or something that's only slightly less. Longer span joists could have higher self-weights, particularly when we get into the DLH series. So with the weight tables, the load tables, all can provide guidance as to what those self-weights are. If there's a doubt about whether the allowance is going to be sufficient, a note to indicate what has been assumed, and instructions to the joist manufacturer to add self-weight, and excess of that allowance is appropriate. So that's better than leaving it off entirely and a note saying that it has to be added. But if the assumption for some extremely heavy and long span joist was, say, 12 PSF, then a note to that effect could be wise, and the manufacturer can check or add a little bit more if the self-weight exceeded that limit. When specifying joist girders, it is expected that the self-weight of the girders is included in the specified KIP designation. So that's sort of the default. However, there are instances where it hasn't been included, and the joist manufacturer could add it, but then it needs to be clearly noted on the design drawings so that the manufacturer takes care of that. And if there's confusion about whether it's been covered or not, or the meaning of the note, that will result in an RFI. A couple of notes here about ASCE or LRFD. Joist and joist girders can be specified under either design method. There's no clear or significant advantage of one design method over another for typical load ratios and cases. If there's a slight, depending on the ratio of dead load to live load or how much wind there is, there could be some very, very slight differences, but they're really not significant. If we have an LRFD condition or design method, the joist manufacturer can factor the loads, but clarity is required on the contract drawings to be clear what is already factored and what is not. And as a general guideline, if the gravity loadings are pretty simple and straightforward, then it would be best to just present the loads as factored and have that already accounted for. On the other hand, if there's a set of complex loading combinations and things like seismic loads involved that are going to require the manufacturer to break it down to more load cases, like following ASCE 7, as we indicated early on in this presentation, then it might be better to provide the loads unfactored. Overall, we would ask that you strive for consistency so as not to mix ASD loads and factored LRFD loads in the same drawings. So we're starting to see that pop up sometimes where we're getting a combination of loads and lacking some clarity as to what's factored and what isn't. Some notes about floor joist. In general, floor joists can and should be placed at spacing similar to roofs. There are a number of advantages to fewer but heavier joists, and that there could be some savings to the joist manufacturer and in the joist price about supplying a few less joists, but also there are other benefits in terms of fewer joists to handle and erect. If it's an application where there's going to be field applied sprayed fireproofing, those costs certainly go down if there's less joists. And if we have joists at larger spacings on a floor and a thicker slab, that just creates a better situation for damping and better vibration performance. So it's a little bit counterintuitive because you would think that maybe more joists would make it stiffer, but it's actually the slab that makes a significant contribution, and a thicker slab and joist space a little bit farther apart can be advantageous. A few more notes about composite SJI Series joist. The cost and the benefits of these varies a lot depending on how many studs and what's the actual cost of that field labor to install the studs. But they can certainly have advantages for very heavy floor loads. The span to depth ratio can be as high as 30 instead of 24 for a non-composite joist, so that can be advantageous to gain some headroom. And then a couple things to note about SJI Series joists that could be pretty significant for multi-story construction are that larger rectangular duct openings are possible, what we call a Varendale opening, in composite joists. It's also possible in non-composite joists as well, and that just helps economize on that ceiling to next floor height. Also, some manufacturers are willing to provide a flush framed end, and that would allow the possibility of keeping the top of composite joist and the top of the supporting beam elevations at the same level, and that also allows the possibility then of that supporting beam to have shear studs and take advantage of composite action. A few notes here about bridging. Here's just a photo showing some typical horizontal bridging rows and diagonal bridging rows. It is not necessary to show specifically the lines of bridging on the structural contract drawings. The joist manufacturer is capable and can be counted upon to properly apply the bridging in accordance with the SJI requirements. Something to be aware of is that the SJI does not require the top and bottom chord bridging rows to align, and there are many instances where the joist manufacturer will call for a specific bridging arrangement on the placement plans. So we see two examples in the bottom here that relate to uplift loads, where the spacing's been tightened up a little bit at the bottom chord for economy, or another instance would be for an ESFR sprinkler system that has some specific requirements about maintaining adequate space between the bridging locations and the sprinkler heads. So for these types of examples, the joist manufacturer is going to have to provide some pretty detailed instruction on the placement plans about the bridging rows anyway. Attempting to show them first on the contract drawings and then having us adjust it on the placement plans, you might as well just defer it to the joist manufacturer and say bridging per SJI. Joist primer, a quick note about that. Primer is applied to the joist as a provisional coating. It should not be considered the final coating. It's generally applied by dipping the joist in a large tank, so consequently the coating may have some inconsistencies in thickness and surface conditions. The photo shows some joists that are starting to be sitting outside for a little bit and starting to develop a little bit of rust, not enough to be harmful, but certainly not a pristine, finished coating. So the joist primer is temporary and provisional. A few notes about economy related to shipping. When exceeded, there are dimensional limits for both the height of the joist or the joist depth and the length that will add to shipping costs. A few quick rules of thumb are that joists over 53 foot will start to require flags and permits, and ultimately, if the span's long enough, escort cars. Joists over about 100 feet will require a field bolted splice in order to ship in halves. I said about 100 feet because that's going to vary state by state, and it's also dependent upon access to physically get into the job site. Joists over about 8 feet tall will need to lay flat, and those will become an over width load. And then the maximum shippable depth is a little bit less than 16 feet. So typically the limit is exactly 16 feet, but that's the state trooper running the tape from the outside of all bandings and overlapping joists and chains and everything else. So it's best not to push up too tight to that for the actual depth of a deep joist. We'll move on and touch on a few things related to responsibilities, and what we're presenting here is some excerpts from the IBC, and the specific section related to joists is section 2207, and it provides some guidance on the responsibilities of the specifier and the joist manufacturer and the contract drawings. So section 2207.4 is specific to the steel joist plate drawings and what would be on there. The key point that I want to highlight here is the statement that the steel joist placement plans do not require the seal and signature of the joist manufacturer's registered design professional. So the steel joist manufacturer can provide a stamped set of calculations, and those calculations need to address things like bridging row placement and things like that. But then the placement plan is really a reiteration of the contract drawings for which the joist manufacturer does not have the responsibility, and they're the things that the joist manufacturer is responsible for are contained in the calculation package, which bears their seal, and the placement plans are not, should not, will not be stamped. And the final section here, 2207.2, is just indicates some of the responsibilities of what needs to be shown on the contract drawings for the joist manufacturers. We've already touched a lot on a lot of those things through the course of this presentation. Next topic is just to highlight a few tools quickly. The Steel Joist Institute website, which is just steeljoist.org, looks like this and has a bunch of different resources. Specifically, we want to call your attention to a Design Tools tab and tell you what's there. This just shows all the different titles that are available. There's a roof bay analysis tool, floor bay analysis tool, some connection design tools for MoMA connections. Virtual joists and virtual joist girders are some tools to plug into structural modeling software to help simulate. The concept is to use the capability that's already there to build a one-off or unique beam eye section to kind of use that to represent a joist or a joist girder. There's also a joist investigation form to help with historical joists, and a tool around floor vibration analysis. And this is just that listing might be a little easier to read than all those blocks shown on the previous slide. The two I want to highlight here in the next couple of slides are the roof bay analysis tool and the floor bay analysis tool. In the interest of time, I'm not going to try to read off the numbers or explain all about how these tools work, but I want to emphasize the fact that they're free and they're pretty comprehensive. The floor joist tool can check the combined joist deck and slab system, and you can look at joists as being either composite or non-composite. And the primary point to make for this presentation about specifying steel joists is that the spirit of these tools is to look for economy, but as you see on the right-hand side, there's a whole list of checks that are being done. So if you want to know if you've made a good combination or a good selection, both for economy, but also that you've properly specified them, this tool can be a great asset because it's all automatically performing all the different checks that you see here on the right-hand side. Similarly, we have the roof bay analysis tool. Again, it's free. It looks at the combined joist and deck system, and it also has a great feature in terms of the ability to do, after doing the initial analysis, then carry over to a new tab and do a check for ponded water. So that's pretty powerful. And again, we see that besides providing cost results, and here we see side by side where different scenarios can be reviewed and boiled down to an approximate cost, weight, and cost per square foot. We see on the right-hand side, again, a whole host of error checking has been done, which is pretty good and will help make sure that the joists are properly specified. In addition to the specifications and documents we covered here and everything in this presentation, we're going to call your attention to the Steel Joist Institute Technical Digest. These are a series of publications related to specific joist topics, which supplement the specification code of standard practice as great resources to consult when specifying steel joists. So there's some listed here, and on the next slide, a few things I'll call your attention to is that in conjunction with the roof bay analysis tool, the publication with regard to ponding loads was recently updated last year. Coming up this year is the Technical Digest number 8 on welding is heading to the printer and will be available soon. So that's just an update from the version that was last published in October of 2008. And then the next one that's in the process of being updated is Technical Digest number 12 for evaluation and modification of steel joist and joist girders. And so that sort of, to summarize the whole presentation, time limits of the presentation didn't allow us to fully explore all of these topics, and there were some other topics that didn't make it into the time limitations. But please feel free to contact any joist manufacturer for more details or for advice about how to proceed with any particular situation you may encounter on your next project. And with that, we are done, and I think we'll open for questions, and maybe Michelle will review the polling question answers first. Thank you.